So the first talk from the is the talk of Sudeep Podder from Indian Institute of Technology, Madras, and the name of the talk is A Theory of Real Grassmann.
So, yeah, first of all, I would like to thank Professor Masuda and Shintaro. So, actually, I must thank a little more than other speakers because my topic is not much related to toric stuff, but still they have given me this opportunity to talk. So, this is a joint work with my supervisor, Parameswaran Shankaran. And so, let me denote the Grassmannian of k-dimensional vector subspaces of Rn by G and K. So for k equal to 1, these spaces are just real projective spaces of dimension n, and the k-ring of these spaces were computed at the early days by of the development of the theory by Frank Adams in his famous paper vector fields on spheres. So, but the theory has developed very much, and unfortunately, and as he said yesterday, that fortunately these spaces, their k-ring is not available in the literature. So we took up this problem. So first, let me start with this power bundle from OK to VNK to GNK. This VNK is the Stiefel manifold of k frames, k orthonormal frames in Rn. And then to GNK, there is this canonical map which sends k orthonormal frame to the subspace it generates. And then this is a fiber bundle, and this lets me write GNK as the homogeneous space On modulo OK times On minus K. And for some reason, it's better to work with a connected group. So we'll write it as a quotient of SON, where this. Hello. Hello. Is it audible? Right? Okay, so this subgroup S of OK times On minus K. So these are matrices of the form so that A is from OK and B is from On minus K, and this so so this is my subgroup S of OK times On minus K, and so this says that I'm interested in the K theory of homogeneous space. And so let me go back to the literature. So K theory of homogeneous spaces were initially studied by Atiyah and Hijrebrook in their introductory paper, where they introduced this K theory. So let me first say that if H is a compact Lie group and X is a compact Hausdorff space, and there is a principal bundle, so X xi is a principal bundle over X, then I can define a map given any complex representation V of H. I have a vector bundle principal unitary bundle over X, whose total space is defined by this total space of xi twisted product with V. So this action we yesterday also saw in Grigori's lecture. So this lets me define a map from the representation, complex representation ring of H to the K naught of the H space X. And this map is actually a homomorphism. So what it implies in the case of homogeneous spaces, I have a so if H is a closed subgroup of a compact connected group G, I have this canonical principal bundle. And so this lets me define a canonical homomorphism from RH to K naught of G mod H. So what Ate and Hijrebrook they proved that if G is not E6 or E7 or E8, then if H is of maximal rank and also connected, then this K naught of G mod H is a free abelian group and K1 of G mod H is trivial. So this they proved using the Chern character homomorphism and this Atiyah Hijrebrook spectral sequence. So and they conjectured that if pi1 G is free, torsion free, then this map is a surjection. So PT showed that. So this theorem is due to PT and this conjecture was due to Atiyah and Hijrebrook. So show that if H is a connected subgroup of maximal rank and they have a common torus, maximal torus T, so that the order of Weil group of G divided by the order of Weil group of H is bigger than 1 plus rank of G and pi1 G is free, in that case alpha is indeed surjective. And he also have given the formula for, I mean, computed explicitly the K ring of G mod H to be RH tensor Z over RG. So this module structure here is given by so RG. So I'll call this map rho. This is just the map induced by the inclusion on the complex representation ring. So what is so in our case the problem is that this subgroup S of OK times O n minus K, this is not a connected subgroup, and on top of that its identity component that is also not of maximal rank in some cases. So let me just say that in the maximal case, this RG tensor RH tensor Z over RG, this can be written as tor 0 RH comma Z over RG. So this is actually PT actually proved this theorem by proving some sufficient condition for the convergence of the following spectral sequence due to Luke Hodgkin, who showed that if H is a closed subgroup of a compact Lie group G, then there is a spectral sequence whose E2 page is given by this Tor groups in even dimension and 0 in odd dimension. So here this RG, RH, and Z, they have trivial Z2 grading, that is everything is concentrated in degree 0. And this module structure is via the restriction map. And on top of that, if pi1 G is torsion free, then this spectral sequence actually converges to K star of G mod H. And so what we want to, so this is actually the main tool for our computation. And we want to show that this spectral sequence actually collapses on the second page. There is some special situations. For example, if this Tor groups for P bigger than 1, they vanishes, then this is actually a isomorphism of Z2 graded rings. So our task will be to compute the representational ring of G and H, and then to show that this spectral sequence actually is.
So in this theorem, H is not necessarily black.
Yes. So this is this is actually the click of this thing. If you want to compute for non-connected subgroup, then I think this is the only way to do. also it's not assumed that H is of maximal rank. In the maximal case, PT actually showed the sufficient condition for this convergence. So, yeah. So first of all, I want to get rid of, I mean, somehow manage this condition, and that can be done by going to some finite covering of this SON. So, so this spin group are double covering of SON, and they are their orthogonal group. Sorry, their fundamental group is trivial for n bigger than equal to 3. So in at least for n bigger than equal to 3 cases, I can just go to spin n and then take the inverse image of this subgroup and express this Grassmannian as spin n modulo this subgroup. And for convenience, I will just write it its identity component also. So H0 is the identity component of H, and this Grassmannian I can express as a quotient of this spin group by this subgroup H. So now what I want to compute is the representation ring of this group, which is quite well known, and of this group H. Yeah, so and the module structure, that is that map rho and the corresponding convergence question. So now I want to concentrate on the case n equal to 0 mod 4. So in this case, actually the center of spin n has a order 2 element which is inside H but not in the identity component. So in general, what happens if n is not 0 mod 4, either the center of spin n is trivial or it has an element of order 4. So in this particular case, actually there is an element of order 2, and I can write H as a product of H0 and this Z mod 2 generated by E. And so the calculation of representation ring is nothing but this RH0 tensor Z theta over theta square minus 1, where this theta is so I have this representation, non-trivial representation of H modulo H0 to O1, and then I have a canonical map from H to H0, and so this gives me a real representation, orthogonal representation, and I am just taking the complexification of that representation. So this is my theta, and so now I want to write. So I'll just explain my notations. So I'll write lambda 1 for the complexified standard representation of SO K. So K here is 2s plus 1, and then n minus k will be 2t plus 1. Yeah. So there I will write mu1 for the standard representation. And when this n is fixed, I will write capital lambda to represent the standard representation of this whole group SON. So with this terminology, we can define the, I mean, we computed the representation ring of H to be this polynomial algebra on lambda 1 up to lambda s. These are just the exterior powers of lambda 1, and then mu1 up to mu t, and then this is just the product of these spin representations for SO k and SO n minus k. So if it is of, I mean, for odd dimensional spin groups, so if k is odd, then I have just one spin representation, and this is corresponding product, I mean tensor product of these. So this is actually obtained by seeing the representation of SON cross SON minus k, sorry, spin n cross spin n minus k, on which minus 1 comma 1 acts as identity. So first thing that we did, we found this representation ring for H, and then the representation ring for G is well known. I mean, these are just since n is even, since n is even, I have two representations, half spin representations, and I can express the uh, representation ring as this polynomial algebra on these generators. So now I want to compute the store groups. So this row map I'll skip, but I want to compute the store group, and it is, I mean, so there is this many generators on this ring, and then this one is also on many number of generators. So to handle this kind of situations, I mean, to make partially easier. So what we want to use this following theorem due to Cartan and So due to Cartan-Eilenberg. So let's say gamma is a commutative ring and C is a gamma module. And lambda, gamma both are supplemented R algebra. So R is a commutative ring with unit, and supplemented meaning I have two augmentation maps, and then I is the kernel of the augmentation map for lambda. So the theorem is that, so if gamma is a projective lambda module via this map phi, and then omega is gamma modulo the ideal generated by the image of I. So I is just the kernel of this augmentation map. For any gamma module A and omega module C, there exists this vector sequence that converges to this store gamma AC. So what I want to do is this gamma is actually a bigger ring, and so I want to take a ring which is quotient of gamma, so maybe on less number of generators, and then if this guy is also concentrated in degree 0, so that means that A is a module via phi over lambda, which is flat, then I mean, it's easier for me to compute. So what I will do, I will just take gamma to be spin n, RH to be A to be RH, and C to be R or Z. Then this vector sequence actually helps me. So what we did, and what was very difficult for us to argue, is that this RH is free over this subring Z lambda 1 up to lambda m minus 2, and then delta plus. So I have taken care of almost all the generators except the last one. And so and this ideal generated by the image of this I is now, I mean, the ideal was just given by lambda 1 up to lambda m minus 2 and delta m plus. I have just subtracted the virtual degree of these representations. So this is my image.
Sorry, can I ask a stupid question?
Yeah.
So those lambda 1 to lambda m minus 2, those are sort of standard representation.
Yeah, so lambda 1 is the standard representation, and lambda up to lambda minus 2 is the exterior power of. Yeah.
And in the first line, why do you put delta m plus minus delta m minus?
Okay, so actually I want to take augmentation 0 classes. So I mean, whatever there are, I mean, whatever references are there, people will usually work instead of lambda, some other augmentation 0 classes are there. They are called pi. But actually our computation became very difficult with those things. So somehow we just made this last thing, which is more relevant to be augmentation 0. Yeah, so now this omega became a polynomial algebra on single generator, and so RH is free over lambda, which says that I can just take RH modulo. This is the ideal generated by these elements inside RH, and so my computation is much easier. So because this omega is now a polynomial algebra on single generator. So in case of polynomial generator, I have this luxury to use Koszul resolution to compute Tor groups, and we used the Koszul resolution since it is a polynomial algebra in two generators. So there will be only two terms, and it will show that the Tor terms for p bigger than equal to 2, those will vanish. So in particular, the Hodgkin spectral sequence will degenerate, and we have this description for the K ring, where this ideal I is generated by the set of elements theta square minus 1 and 2 to the power m minus 1 theta minus 1, and there is this relation. So this is actually coming from the restriction homomorphism rho. So rho will restrict this lambda i's, capital lambda i's, to this product times some theta j times this product. So this is coming from the image of this ideal inside RH, and then this theta square minus 1 is coming because of this calculation we did of representation ring. And so this is the description of K naught, and K1 is the ideal generated by theta plus 1 in the ring S modulo I tilde, where I tilde is generated by everything except for this. So it's kind of, we are getting K1 as the annihilator of this element inside this ring. We wrote a RH modulo this ideal image of ideal generated by I. So this is our result in the case of case when n is 0 mod 4 and k is 1 mod 2. So yeah, as I told, in the other cases we cannot express this thing as a product, but still that so it's a semi-direct product, but yeah, we could, did not calculate the representation rings explicitly. So what we did, we used some other arguments, Chan character arguments, to compute some part of the, almost the K ring of this G mod G and K. So I have gamma nk is the canonical K plane bundle over G and K, which over every plane the vector space is just that plane, and I take the complexification of that bundle, and K and K is the lambda subring of K G and K. So this is the K ring of G and K. This is the subring generated by this complexification of these bundles. So this bundle. So our result is that this map from K and K to K G and K. So for K between 2 to n minus 2. So as K equal to 1, this case is just, I told that it's RPN. So this has a finite co-kernel, and so yeah, I have little amount of time. So I have expressed this K and eta, sorry, this should be n minus K as 2s plus 1 epsilon 1 and 2t plus epsilon 2, where epsilon 1 and epsilon 2 are in either 0 or 1, and then pi and qj are the rational Pontryagin classes of gamma nk and gamma power of nk. So this is the description of the cohomology algebra of G and K with Z half coefficient. And so from here, what we see that so this odd dimensional cohomology is either trivial or generated by a single element as even graded submodule. So what it says that either K0 is K1 is free abelian, or in when this is not non-trivial, then this is a module generated by one element over K0. So we have this map from K K tensor Q to K K. This should be K G N K tensor Q to H even G and K, and we have shown that this map is actually surjective, so that the map from K and K to K G and K, that has a finite co-kernel. So for that, So this gamma NK, some gamma NK park, this is a trivial bundle. So this Qij's, this Qij's here can be expressed in terms of Pij, because this sum of these two bundle is trivial. So what we did, we have shown that this Pij, these Pi's are actually in the image of this above map. So there is this Chon character map from KGNK to H even, and then there is this map inclusion. So this should be KGNK inclusion tensor identity. We have shown that this is a surjective map by showing that this Pi's are in the image of the map. Yeah. So these are based on this paper, which is to appear on homology, homotopy, and application. And these are some references. So thank you.
Question, why are these limitations
For complex Grassmannian, I know it is known. For real Grassmannian, I'm not sure. I think it is. It should be there.
you will have more more terms to do.
Yes.
More than 8.
Yeah.
And question. So that's spectral sequence Cartan Ellenberg.
Yeah.
Is it kind of like branching deep spectral sequence measuring creativity of operators?
Yeah, actually, yeah, I must say that I have just used this spectral sequence, but
So basically, my question was, is this spectral sequence coming from some complex?
yes, it should be, yes.
Maybe spectral sequences.
Yeah, these two terms are coming, maybe, yeah, just because.
More questions? Same.
I was given it to them. Oh, 245. Okay. 20 minutes break. Yes, I certainly like to take a call. Yeah, I have heard for that there is some computation has been done by Google.
And there is another paper by someone called. There is the paper is not. What is that? Why is that not available? And maybe where I see that paper will answer. From your here you can go stars. Expected to get some other no, by somewhat. Yeah, we completed for this. So this is on one generator and then two well, I think for I mean, using the API framework, one can include the.
If somebody has a USB, you have a USB stick for
Yes.
volumes. I'll copy mine.
Really? I collect all the and one there are all different parts here I use and all of your this is my I take the train.
One.
So I take the empty that as the and it's like about one order.
Sorry, but.
1, 4, 3, 3, 2,
Yeah.
1, 3, 2, 1, 2. The other type. Another type. Corresponds to the train. And 1, 4, 3, 1.
So these are steps that
This one is another.
diagonal.
Well,
Diagonal is beyond.
1, 3,
Yeah. These are.
And finally, doing one is
Yeah. You want to.
Maybe you. I was very.
Yeah.
Anyway, during the thing at first, because you know, I was totally doing it. So I checked my conversation. So I checked. You know, there are too many. Holidays then. I writing or not. Yesterday night, but maybe they are all.
This guy is the basis of. The basis of. They. That's how we do it.
Yeah, I was wanting to make it say. It's completely different now.
Thank you. Thank you.
It's open eye for you can change by some. The PP change some.
I very,
This will be also change.
you know,
But the alpha.
I'm a mathematician. If
Alpha I have a
forward to that history, you were seeing that.
Right. After this, parameter is constructing.
Very well.
I used it to copy the thing.
Anyway.
The alpha I give my.
Oh, yeah, that's something. Alpha.
One page.
Section.